Thanks, Nell. Thanks, Beck. It's an honor and privilege to be here to open up the conference with the first keynote. I've got a talk here today that it's about Microsoft's journey with Rust, what we're doing, where we're going, how we're doing it. But it really starts with us looking at cybersecurity from the perspective of what is causing vulnerabilities in our systems. Microsoft's been tracking this through Microsoft's Security Response Center for close to 20 years. And one of the things that we've seen just consistently is that for Microsoft software, roughly 70% of the vulnerabilities historically have been due to memory safety issues. That's, of course, because lots of Microsoft code has been written in C and C++. For legacy reasons, for systems reasons, a lot of code in Windows and kernels and even the cloud can't run with garbage collection. And so we've been relying on C and C++. Rust comes along and promises to solve this kind of problem for us. And one of the things that I realized a long time ago is that no matter how much we really want to make C and C++ better, we can't make it as good as what Rust starts with. And so this is kind of the tweet heard around the world, where back in 2022, I'd seen a list of popular programming languages, and TypeScript had risen, and I followed a tweet on that one with this one, which was, speaking of languages, it's time to deprecate C and C++. And for cases where you can't tolerate garbage collection, use Rust. This is one of the most engaged social media posts of my entire career. And it prompted an email a few hours later from Satya Nadella, the CEO of Microsoft. I had not cleared this with PR. I had no idea it would blow up like this. And he asked and added some people to it. You can imagine the people at Microsoft that he added that were relevant here. Are you serious about this? Are you convinced that this is really what we should be doing? And I responded, yes, I do. And I gave him a lot of evidence of our adoption already at that point. And he took that, and we've adopted a Rust-first strategy at the company. In fact, that tweet, though, I had, a few weeks later, had support from other areas, like the National Security Agency. A couple months later said, it's time to shift to memory-safe languages and away from C and C++. And around the same time, Linus announced that Rust would be supported in the Linux kernel. So I had a lot of good company in this direction. And Microsoft's commitment, it goes above and beyond just saying Rust is great. We're putting it as part of our official strategy. This is the Secure Future Initiative announcement blog post from roughly a year and a half, 2.5 years ago. This is where we said we're going to actually make a commitment to shifting away from unsafe languages to safe ones wherever we can. And we've been supporting this financially. We were a founding member of the Rust Foundation, and we've made significant contributions both directly like this, as well as indirectly through OpenSSF and Alpha Omega. So let's talk a little bit about how we've been adopting Rust, where we've been adopting it, what we've learned as we've gone along. I'm going to talk about adoption in Windows. I'm going to talk about adoption in Office, and of course in Azure. And then I'll talk about a little bit about our developer feedback as we've done adoption of Rust and what we've done to make adoption easier for our developers. So starting with Windows, one of the first places that we want to focus Rust is in places where we can't tolerate garbage collection, and it's security critical software. And of course, that includes UEFI, the firmware that boots Windows devices. Specifically, we ship our own UEFI in Surface laptops and desktops. This is where we have implemented an open source UEFI implementation in Rust called Project Mu. And we've also made it easier for our OEM partners to write UEFI modules in Rust as well. So this is an example of us starting with core components that are small, need security, and will lift the security of the entire ecosystem. Another place that's very security critical, and Beck mentioned this, is Russell's and TLS. So we're fully behind getting to Rust-based TLS. Has to be high performance. You don't want to have garbage collection happen there. And we've integrated or provided support for our SymCrypt cryptographic library that ships as part of Windows, and it's also now available in Linux, to support Russell's integration. I'll have more to talk about SymCrypt towards the end of the talk. But when it comes to mainstream Windows, one of the first areas that we said, we really want to get Windows moved over from C++ to Rust. Where can we start? And one of the first places we decided to start is a fairly large code base, one that historically has had a lot of vulnerabilities, one that's fairly self-contained, and one that ships outside of Windows where we can ship it independently of the Windows core. And the candidate we found here is the direct write core, DWrite, which has font parsing and font rendering, been common cause of security vulnerabilities from the start of Windows. So we started, you can see 2 developers took on this project. In 6 months, they'd ported TrueType with 154,000 lines of Rust code and had it compiling and running in Rust. And we've been incrementally adding more and more Rust support in the DWrite library. So it's becoming Rustified even as we speak. We also saw performance improvements, and this is pretty consistent. Whenever we take a C++ code base and port it to Rust, we often see a performance improvement, potentially partially because of just better code hygiene as we do the port. But fundamentally, Rust adoption doesn't come with any kind of performance penalty. Now, we said that was a success. Let's go deeper. Win32k.sys has been there from the start of Windows. It is where the graphics subsystem and the windowing subsystem live. And the graphics system, GDI, has been the source, and both of those have actually been the source of pretty much nonstop kernel vulnerabilities that have resulted in elevation of privilege problems for Windows. Almost every month on Patch Tuesday, you can probably find a bug that we're patching in Win32k.sys. It is like the oil well, the underground oil repository that is leaking oil up a few drops at a time, just consistently. So we said, let's go see if we can start to get Rust in the kernel, starting with the highest risk surface area of Windows, this part. And you can see that we've now implemented a core component, the GDI region code, which has been itself the source of many of these vulnerabilities, and have ported that to Rust. And that is actually shipping now, officially, in your Windows systems if you're running it. You can go take a look in your Windows System 32 directory. And if you do a directory listing, you will see there a file, win32kbase _rs.sys. That is the Rust implementation of Win32k components, starting with the GDI region component and moving on. Now, adopting Rust doesn't mean you're not going to have bugs. But what it does mean is that those bugs are very deterministic and very controllable. So yes, of course, we hope that we're not going to have more blue screens as we move code to Rust. But one of the things that we get is when we do have a problem, in fact, this region code had a bug that external security researcher found and disclosed to us that caused a crash. This crash, you can see, is a very deterministic crash. It's Rust detecting a memory out of bounds read and crashing the kernel. This we view as a success. This code, written in C and C++, this bug would have actually resulted in a potential elevation of privilege, as opposed to a blue screen crash that's very deterministic and can't be exploited. So it's an example of already we're seeing success in the adoption of Rust in the Windows kernel. We also want to make it possible for our partners to write their own Windows kernel code in Rust. And so we started this project here, where we've created FFIs for the Windows driver model so that our OEM partners that are writing drivers for their hardware can now start writing them in Rust. This is still experimental, but we plan on making this an official way to develop Rust drivers for Windows in the coming months. Now, let me talk a little bit about Rust in Office. Now, Rust in Office. So Office is also a large application, but it also consists of services. Services that run at massive scale. Now, one of the problems running at massive scale with millions of documents is that you want to go find documents quickly when you're doing search and when you're doing other kinds of analysis that the user wants on their data. One of the ways that we do that is with semantic search. And one of the projects that came out of Microsoft is something called DiskANN. DiskANN stands for Disk Approximate Nearest Neighbor. Approximate Nearest Neighbor is a semantic semantic search algorithms. They create graphs of semantic embeddings, and then when you perform a query on it, you get back results that are relevant. Bing adopted DiskANN. They were doing queries at order 100 nodes in a graph, so much smaller than what Office needed. Office wanted millions of nodes in the graph. They realized that the implementation of DiskANN in C just wouldn't give them the scale and performance that they wanted. And so what they decided to do, as one of their first projects that they really were taking a big production dependency on for Rust, was to rewrite this component in Rust. And so they've ported DiskANN to Rust. DiskANN in Rust is actually open source, so you can go to the DiskANN repository and find the Rust implementation. It supports order million nodes in a graph queries. And you can see that when we compared the performance of the Rust implementation with the C++ implementation, here on this graph, you see queries per second as the y-axis, and you see recall, or the accuracy of the search, on the x-axis. If you want to spend more time in the query, you can get better accuracy. And you can see that for the same amount of time you spend, the performance, the accuracy, is much higher for the Rust version. So we saw tremendous wins, and we also see reduced memory footprint, too, with the Rust version over the C++ version. So this is actually considered another major win. And the Entertainment and Devices division is actually all in on Rust. In fact, one of the things that they like about Rust over even over garbage-collected languages, which are memory safe, like C#, is the concurrency correctness of Rust. And so for cases where they've got code that is very asynchronous and has concurrency potential issues, is that they view Rust as superior even to C# for those kinds of cases. It's also, they love the performance they get because that makes our systems more efficient. So Office, all in on Rust. Now let me switch to my home territory, which is Azure. As Deputy CISO of Azure, and actually officially that title was given to me about 1.5 years ago. I was voluntold that I was Deputy CISO for Azure. But I'd actually been operating in that unofficial capacity since I started in Azure. Of course, my interest in cybersecurity, realizing that security is fundamental to a cloud platform that's successful, made me very invested in security. And that's why, for example, you saw me make that tweet. And I'd actually, even prior to that tweet, told our teams we should stop new projects in C and C++ and start with Rust if we can't tolerate a garbage-collected language. So that philosophy is actually the longest-rooted philosophy of Rust inside the company. I didn't really have the authority to declare that. I had the influence to do it. Now, as DCISO, I can tell the teams officially there's just too much risk in adopting or creating new C++. You will not do it. And so here's some examples of our adoption of Rust in Azure. And one of the first places, and obvious places to adopt it, is in security-critical components. Again, they can't tolerate garbage collection. And a great example of that is in the platform root of trust. The root of trust is what boots the system, measures the components, and launches it securely according to some policy. A few years ago, we started working with industry partners like AMD, Google, and others to define an open source, and not just define, but create an open source root of trust. That is called Calyptra. It's part of the Open Compute project. And right from the start, we said, we're going to do this thing in Rust. So if you take a look at the ROM of Calyptra, this is all open source. If you take a look at the firmware of Calyptra, if you take a look at the emulator for Calyptra, they're all written in Rust. Now, another place that is very security critical is on our offload system. We call that Azure Boost. And what an offload system is, that's common to every cloud provider, is that we have an SoC, ARM-based, that sits on the side of the server. And that's where we run our control software that manages the server, that does offloads for network and disk. And this is another place, and actually the first place, where I said, hey, as we're creating new agents for Boost, they will be written in Rust, not in C++. This is a place where all the code is native or non-garbage collected. A lot of the code is just the teams have voluntarily taken their agents and ported it. But one of the things that we've said is that for any code that is touching untrusted user data, like we have an instance metadata service agent that sits there that is taking requests from the virtual machine to ask things about the environment it's running in, where we also give it back, for example, security tokens, where we're getting certificates from the virtual machine. That is code that we've ported to Rust, because that has to be safe and secure, as opposed to doing all that kind of parsing and handling of those connections in C and C++. So every place that we've got untrusted input handling, the mandate is rewrite it in Rust, and any new agents are written in Rust. And like I said, there's been such enthusiasm for Rust as people have gotten started that they're porting existing agents from C, C++ to Rust, even if they don't fall into those categories. But another place where security is extremely critical is in our hypervisor. That is where it implements the security boundary for the Azure platform. If that gets breached, then we've got a big problem, because the threat actor can get onto the servers themselves. So Hyper-V is one of the most secure pieces of software that Microsoft's ever created. It's undergone amazing amounts of fuzz testing, validation, code reviews, and real-world, of course, penetration testing by many of our customers. Not the kind of customers we necessarily want, but many of our customers. So one of the things, obviously, this is a great candidate to move to Rust. And we've started that move incrementally. This is a very sensitive piece of code. It's obviously, we need to be very careful. And it's also code where it's hard to take chunks and implement them in Rust, given the interfaces with the rest of the system, which is written in C, C++. But we have started that. And in fact, that's shipping in Azure, even as we speak, this rollout of a new version of the host operating system, which then gets released as the next version of Windows Server and client, has ARM64 emulation support on the ARM64 platform, instruction support, implemented in Rust. So that's the first step. So we're officially now shipping Rust as part of Hyper-V. And this is just a place where you'll see continuing growth of Rust in that component. And speaking of hypervisors, there's the hypervisor itself, and there's the virtual machine manager. So that's another system that we started, and we started by creating this in C#. Actually, let me take that back. We started this project in Rust from the start, OpenVMM. In fact, there's a core group of people in the kernel team in Windows that are Rust enthusiasts. And so new projects like this, we needed an open virtual machine manager that sits underneath the virtual machine on Azure hosts and talks to Azure Boost. This is where we run, for example, emulated network adapters that connect to the Azure Boost network adapter, so to provide compatibility with existing operating systems. That system is a Linux system. That system runs an open virtual machine manager that's written in Rust. OpenVMM demonstrates Microsoft's commitment not just to open source and Rust, but to cross-platform portability. So OpenVMM is compatible not just with Hyper-V, not just with Windows, also with Linux, and also with KVM. And this is completely open source. So another place that we started, and this one started as a C# prototype, is us looking at isolation of sandbox code. And virtual machines with virtual machine managers is great when you've got a full operating system. But there's cases where we just want to run a tiny piece of code. For example, a user-defined function that sits in a network path on a front door, which needs to process some of the network traffic in a very lightweight way. Maybe perform some transformations on it, maybe perform some security checks. We don't want a full-blown hypervisor with a full-blown operating system to do that. It's just we just want to run the code, which is untrusted because it might be coming from a user, inside of a small sandbox. And so as a prototype, we developed something that has eventually become Hyperlight. This is a tiny, lightweight sandbox that is small enough to support WASM, or even just a precompiled binary that can run inside of basically a virtual machine boundary without an operating system underneath it, only with APIs that are provided by the host of Hyperlight to the code inside that Hyperlight isolated virtual machine. And so Hyperlight, we wrote it in C#. We then ported it to Rust. This is able to launch virtual machines in just under 1.5 milliseconds with a full piece of code in it. And so this is actually part of our Azure front door, where we've got Azure Edge Actions, which allow you to go deploy, like I said, user-defined functions on our network gateways. And that is being supported with Hyperlight, written in Rust, which is, of course, open source as well. And there's a talk, I think it's tomorrow, on Hyperlight that will go deeper into how we developed it. And then another example is Azure Data Explorer. Azure Data Explorer is our logging analytics system. We process it literally hundreds of petabytes of data with Azure Data Explorer, or Cousteau it's called, across all of our regions. And one of the developers a few years ago, looking at the evolution of this and looking at the security implications of this, said, hey, what if we rewrote the data storage layer in Rust? And so one dev started doing that, and after about a year, had the whole thing ported to Rust. And that went into deployment, and the continuing evolution of Azure Data Explorer to Rust, where you can see the query engine, then got ported to Rust. Now Azure Data Explorer consists of about 2.3 million lines of C# and roughly 350,000 lines of Rust and 350,000 lines of C++, with the C++ shrinking away. And then it is an official language, as of this year, for Azure. An official language for Azure means there's an official SDK supporting it so that you can talk to Azure services from that language. And this is the announcement of the Azure Rust SDK from earlier this year. So how have our developers liked Rust or not liked Rust? You've gotten some impression, I think, by me talking about the enthusiasm that our developers really like Rust. So leading up to this, we did a survey to see what developers like and don't like about Rust at Microsoft. And here's some of the direct verbatims from them in feedback. So they love increased performance. They generally see it. They love getting rid of a whole class of errors. They love the safety part. They love the fact that they write it once and then they're not debugging it for days because Rust forces them to do it correctly. They all love all those things. They love the fact that LLMs are making it easier to write Rust now. And that is just a fact, as AI and Copilot Agent and other agentic AI systems are fluent with Rust, getting more fluent with Rust, and help them develop it more quickly. The learning curve, by the way, it's roughly, we see developers, if they're coming from a C, C++ especially, it's a shock to them. It's like, well, this is a totally different way. It's like coming from going to functional programming languages. Your mind has to shift to adopt it. And that's hard. But we find that, and this is me talking anecdotally to developers, roughly after a couple months, they've actually shifted their mind and now then become one with the way that Rust borrow checker thinks and works and actually enjoy it. So initial shock, work their way through it, and come out the other side in a couple months as a Rust fan. And that's reflected in some of these. Now, there are, of course, what we call opportunities or complaints about Rust. And so here's some of the direct feedback. Tooling support has gotten a lot better over the last year at Microsoft. Visual Studio Code, the Windows debugger have native support for Rust, crashes and debugging. But you can see C++ interop and C# interop, still painful for everybody. You can also see that async debugging is a big complaint. Lots of our code is async, and debugging that is still very painful in Rust. Dynamic linking, you can see dynamic linking will eventually bite us. FFI is tough to do safely even in Rust. And they want the cargo system, and they want officially supported crates, which we've been working on. But overall, is a massive net positive. The developers that even have these complaints don't want to give up Rust at this point. And so Rust is here to stay and embedded and just growing in momentum at Microsoft. We've also shared some things with the public that have helped our own developers. Like we've created a Cargo SDK plugin for Visual Studio to make it easier to bring in Rust components into existing C# and C++ projects. That is open source there in the MS Build SDK repo that you can go take a look at. And so that helps with adoption of Rust. And then we've taken a lot of the guidelines that we've been developing over the years for how we believe we at Microsoft should develop Rust-based code. And we've codified that and published this as the pragmatic Rust guidelines as from Microsoft's opinion. And actually, if you take a look at this, it's really not controversial. Anybody that's an experienced Rust developer will probably look at all of this and say, yes, this all just makes sense and is common sense. Of course, for somebody that's new to the language, a lot of this stuff is just going to help them get started more quickly and fall into the pit of success if they follow these guidelines. There are things like, you can see interoperability, resilience, building the application, defining FFIs. All of this is covered. In fact, we wanted to, it's kind of interesting because I was looking through the repo, preparing for this, and I was wondering how much of this is LLM generated. I don't see that many emojis. I don't see the rocket ship, which must mean that it's human generated. Of course, I get to the end of the repo and the documentation, and it says, this was handcrafted by humans, but here's a one-page version of it that is LLM friendly. So it is already getting ready for LLMs to be able to process this, so you can add it to your Claude.md or copilotinstructions.md and get those agents to start honoring these kinds of guidelines. Now, one of the other things we want to do is accelerate migration. And so we started down a few paths there. One of them with the Symcrypt library. Symcrypt is written in very high performance, hand-tuned, most scrutinized. Of course, this is the most sensitive code at Microsoft, where we do our cryptographic processing, where we do our RSA and elliptic curve cryptography. This code we're rewriting in Rust. So and not just Rust, but verified Rust. We have a verified language project at Microsoft Research that we've got a project that we're using to verify the code that we write in Rust. And to make it easier to interop, we've actually taken it and made it so that we can take the Rust code that we verify and have it transpiled to C++ and go right into the Symcrypt code base for easier interop with the existing C++ code there. But we're also not just transpiling to C++, we've started the rewrite of Rust, and new algorithms like MLChem, which is the key exchange algorithm that's post-quantum safe, is written in Rust. And we're exploring things like this. There's going to be more to come on this. This is just to give you a hint of where we're going, is GraphRAG, which is an algorithm that Microsoft developed for how you take complex pieces of bases of information and synthesize it into a graph of hierarchical knowledge that you can give to an LLM so that it can reason over huge amounts of data very efficiently. We're applying that to coding as well. And so if we take the abstract syntax tree, we pass it through the GraphRAG algorithm and create a graph that semantically represents a large code base, we can have the LLM start to reason over it and port the code itself piece by piece from one language to another. Here's an example of GraphRAG code Rust translator that is taking a Python game. This is just to show you proof of concept. This Python game is a jumping game, and this is just looking at the existing Python files. There's 3 core files in the project. And when we run this, you can see that it's a nice little side-scrolling jumping game. Boing, boing. Now, if you just gave that code base to an LLM and said, go start translating this to Rust, this is what you're going to get. Paste it in there. Here's the code. And we start getting the Rust to come out. And then when we go to compile that code, we copy it and paste it into VS Code. There's the LLM translated code. And this is only a 3-file Python project. You can see lots of problems with this code. Of course, LLMs are going to get better, but they're not going to be able to handle massive code bases. But here, what we can do is just take that, use the GraphRAG translator from Python to Rust, Now we take a look at the translated code. It actually translated the files themselves. So you see the same structure of the project because the LLM understands the structure. And now we go run that. And you're going to see it's going to look exactly like the native Python version. So like I said, you're going to see a lot more of this kind of acceleration with the aid of LLMs of code from existing languages, C, C++ specifically, to Rust over time. And you'll see more Microsoft talk more about that in the coming months. So with that, I want to conclude just by recapping. Microsoft's been invested in Rust from the start, from founding member of the Rust Foundation. Rust is permeating Microsoft's core infrastructure at this point, and it's just going to continue to accelerate. And it's just awesome to see so many people here that are supporting Rust. We love the fact that the other major hyperscalers are all 100% behind Rust as well, and that we're building up this community together to make the world a more secure place, and hopefully getting rid of blue screens at some point. So thank you very much.